Rongchan Zhu from Beijing Institute of Technology, who will be speaking to us about Makeenko-Migdal equations for two-dimensional Yang-Mills from lattice to continuum.
Okay, thanks for introduction and also for invitation. It's my great pleasure to be here, and this talk is based on joint work with Shen and Scott Smith. And the reference for my talk is already on archive. So we start from this lattice Yang-Mills model on epsilon ZD. Here we consider this is our lattice model. And here, compared to the
Good luck. And now we consider on this lattice model, on each bound we have a random variable, this qxy, and qxy we're taking values in this Lie group. So this Lie group is just here we can choose this Lie group as this UN or this SO1, this unitary group, unitary matrix, or this orthogonal matrix with determinant equal to 1, or this SUN. And the reference measure is this product of this Haar measure. And here we consider this Z, this partition function, makes this is the probability measure, and S is our action functions. And here we consider this Q is our configuration space. And in fact, to define this lattice Yang-Mills model, we need to first fix this finite volume lattice, and to define this measure as this Gibbs type measure. And since this Lie group is compact, we can easily use the tightness argument to extend it to the whole infinite volume limit. But whether it's unique is still unknown. And the action function is given by this S depending on its Q component, depending on its Q. And here we have this coupling constant. One is depending on this epsilon. Here epsilon to the power d is the parameter for this integral. And the epsilon to the power -4 is, in fact, this action function is just given by some discrete derivatives. So this epsilon to the power -4 just can be viewed for these derivatives. And here this n is the same constant n for this un here, because this is to study the larger limit of this.
I think everyone show it once.
What's that? Study the larger limit of this Yang-Mills model, and compared to the usual this bin system. Now this label, the index for this model is given by this bound xy. So if we change so for this is. So this is our lattice model, and now here we have this coupling constant, but we also can add another coupling constant beta. Here we just choose this beta equals to 1 for simplicity. And here we also have another part depending on this Q component. As I just mentioned, if we change the orientation of this bound from xy to yx, it's qyx just equals to the inverse of this qxy. And now, for this action function, it's just the real part of the trace of the identity minus this QP. And this QP is just the product of this Q component along the boundary of this plicat. So the plicat just, this is the example of this plicat. So this is the square bounded by these 4 bounds. So this QP just means this QXY, QYZ, QZW, QWX. And we just take the trace of it. So this gives us these action functions. So from this action function, this is like the usual Gibbs measures. We can see this QP will have large probability to close to identity. So this is the usual this Gibbs measures.
And an important property also mentioned in Elias' talk is about this so-called this gauge symmetry. And in the discrete case, we also have a discrete version of this gauge symmetry property. This means for any g-value function, this Lie group value effect function from this all the vertices on this VD, we can do a gauge transform for this QXY. On the left, we multiply this gx, and on the right, we multiply the inverse of this gy. If we substitute this gauge transform into these action functions, we can see here, if we substitute it, and the inverse of this gy and this gy will cancel to each other. And finally, we only have this gx and the inverse of this gx. And by using the second invariance of this trace, in fact, all this gx and inverse of gx will cancel to each other. So in this case, this action function will not change under this kind of gauge transform. And this is this discrete lattice Yang-Mills model. And we also have this continuum, this Yang-Mills model, also mentioned in Elias' talk. In fact, for the discrete one, this Q component taking values in this compact, this Lie group. But for the continuum case, this Yang-Mills model, in fact, as I just mentioned, this QP will have large probability close to identity. And for each QXY, it's also, in fact, should be close to identity. And the continuum gauge field, in fact, measures the rate or the changeable rate of this Q close to this identity. So this, in this case, this Yang-Mills measure in continuum case, its field A is given by a one form. So each component, this AI, will also take in values in the related algebra. And we also have this Yang-Mills measure formula given in this way. And this action function is given by this L2 norm of this curvature pattern. So this FA is given by this differential of A and this Lie bracket of A. And also, this can also be written in terms of this components of A components. So here we can see this FA depends nonlinearly on this A. So this also makes this action function, in fact, is it's nonlinear depending on this A component. And we already know, in fact, even in two-dimensional case, if we consider Gaussian free field, it's not a function but a distribution. So for this Yang-Mills measure, it's more complicated. So it's also a distribution. How to make sense of this measure should be a problem. And in this two-dimension, and in this case, we also have this gauge symmetry property. This is like the continuous version of this gauge transform. It acts on this A component. And for any g-value function g, we have this continuous version of this gauge transform. So it's given by this adjoint given by this g component, and also the differential of this inverse of this g. This also appears in this Elias talk. And if we substitute this kind of gauge transform into this FA component, we will find the L2 norm of this FA part will not change. This is the environment under this gauge transform. And the relation of this continuum, this Yang-Mills measure, and this discrete, this lattice Yang-Mills field relation is given by, as I just mentioned, by using this exponential map. So if we consider EJ is just the coordinate basis in the Euclidean space, we consider this is our Q component, and it can relate it to A component by using this exponential map. So if we substitute this formula into this discrete, this action function here, as I just mentioned, so this term is just like some discrete version of the derivatives. So in this case, we have this epsilon to the power minus 4. So this part, in fact, will converge to some derivatives of the A component. And and here this A component taking values in the related algebras, they do not commute, so they will this will gives us this the bracket. So finally, this will convergence to this L2 norm of this curvature form. This, as I just mentioned, in two-dimensional case, how to give a meaning of this measure should be a problem. It's not a function, but a distribution. In two-dimensional case, this measure has been studied a lot in the literature. In this morning's talk, in Ilya's talk, he mentioned a lot of literatures. I just list a few of them. One important work by Bruce Driver is he can using one so-called this actual gauge. So actual gauge just means we can find a gauge transform. If we consider this in a discrete case, actual gauge means you can find a tree on this lattice such that the Q component on this lattice can be identity. So in this case, we can find a tree like include all this vertical lines. So in this case, we can make all this Q component along this vertical lines to be identity. So and we just mentioned this A component is like the increment of this Q component. So all this A component for this second, we can consider for this, if we consider on the two-dimensional case, so this A2 can be equals to 0. So in this case, this Lie bracket is also 0. So this F component will depend linearly on this A component. So it means we can view this FA view it as the algebra value of the white noise. And A can also be seen as the integral of this white noise. So based on this idea, in 1989, Driver just used it to give the joint law of this gauge invariant observables called this Wilson loop on this R2. And later, Gupta has extended his result to compact manifold. And based on this Driver's formula, Terry has studied a lot of interesting properties for these Wilson loops, such as larger limit of this kind of Wilson loop. And more recently, because this Driver derived his formula based on this actual gauge and give the joint law of this Wilson loop. And Ilya also studied from this lattice approximation, and he can construct a random connection A with better regularity and using this rough path approach. And more recently, by this Sheffield Park and others, they also using based on this Driver's formula, they can represent this expectation of this Wilson loop in terms of the sum of some random surfaces. But all these techniques are based on this actual gauge. So if this works very well for the two-dimensional case, but for general model, if we consider Yang-Mills model coupled with the Higgs component, or three-dimensional case, this trick will break down. So recently, there are other approaches, as also mentioned in Ilya's talk, based on this stochastic quantization. If we consider related Rongchan dynamics, then we can using or develop the theory of the regular structures to consider the Rongchan dynamics for more general models. And in this case, as mentioned in this by this A.J. Chandra and Ilya, and also Hayo and Hall, they can construct find the local in-time solutions for this Rongchan dynamics for the two-dimensional and three-dimensional case, like Yang-Mills Higgs measures. And their solution will satisfy these gauge covariance properties. And here they're using this regular structure theory to handle the small-scale problem. Because this gives us a nonlinear PDE, and using regular structure, they can they have a systematic way to handle the related renormalizations.
But the solution in these two papers are still local in time. In their further work, Ili and Hao, they can also construct global in time solutions of the two-dimensional case, and for this 2D Yang-Mills measure. And their argument is they using this random connection constructed in this paper, and also using this lattice approximation and also Borgen's argument to construct these global solutions in this case. And more recently, by this Brinkman and Chao, they do not use this measure, but they're using a pure more PD argument. They combine this PD argument and power control calculus. They can consider for the abelian case. So means this Lie group is just U1 and coupled with this Higgs component. So they can use them to construct global solutions for this global in time solutions for this dynamics. So this gives PD construction for this abelian Higgs models.
Just in 2D.
Yeah, just in 2D. But if we, this is for the continuum case, but on the lattice we can also consider related dynamics. But in this case, this field only taking values in the Lie group is compact, so we can do more. So joint with Hao and also Xiangchan, we can consider for this lattice Yang-Mills model, if the coupling constant here, we consider still this lattice Yang-Mills model, but with epsilon equals to 1. And we have beta. Beta is independent of this independent of n. And if beta is small, we can prove the related some log-Sobolev inequality for this lattice Yang-Mills model or lattice Yang-Mills Higgs model, or some Planckian inequalities. And in this case, because this field taking values in the Lie group, so we can use curvature and Bakry-Emery to derive such kind of result. And using this kind of result, it also implies this mass gap properties for this lattice Yang-Mills model. So this means the correlation functions of two different local observables, we can see just as this Wilson loops will decrease exponentially with respect to their distance. And we can also use this kind of functional inequality to derive the marginal limit of this Wilson loop is just given by some deterministic functions. And this is for this applications of the dynamics. But today I'm not going to talk more on this dynamics. I want to talk about more on this Wilson loop for the two-dimensional case, and the techniques were based on this driver's formula. So first we recall what is the Wilson loop for the two-dimensional case. For the discrete case, this Wilson loop is, we fix the loop. Here we consider this is like this L epsilon. So Wilson loop is the product of this Q component along this loop. Since here this is a loop, so we can see this Wilson loop also satisfy this gauge invariance property. So this is interesting, this gauge invariant observables. And here we consider this Q taking values in this Lie group is like this UN. So in fact, the trace of this part is of order n. So here we also have another constant, this 1 over n, such that this part is of like order 1. We can study the larger limit of this kind of observables. And for this kind of Wilson loop, there are also interesting open problems for higher dimensional case. One is called this aerial law. To prove it for all this coupling constant, expectation of this Wilson loop will decrease exponentially with respect to the area of this loop for general this Lie group. And another is to prove for all beta this mass gap or larger limit.
All these results are true for two-dimensional case because two-dimensional case we have this driver's formula, so we can find the joint law effect of this Wilson loop. We just given by some like this heat kernel, so we can prove this area law, this mass gap. In fact, if we consider two loops, they are not intersect. In fact, they are independent. So in this case, for two-dimensional case, pure Yang-Mills case, this result already has been studied a lot in literature. But for higher dimensional case, we can ask the same question, but it's still a lot of questions still unknown. And for the continuum case, we also have this Wilson loop. For the continuum Wilson loop, here we just draw an example of this loop. So it means, for example, we start from this vertex V, and it go along this way. Yeah, we can consider more complicated loop or simple loops. Here, and then it go back to this V. This is just some simple crossing vertex here. And in this case, formally, we can also define this Wilson loop. So it's also the trace of this Q component along this loop. But in this case, this Q component formally is also given by the exponential of this A component. So it's just a product of this exponential of this A component, and we take the trace. However, as I just mentioned, this A is not a function but a distribution. How to give a meaning, and this product is for infinite points, they are uncountable. So how to give a meaning to this Wilson loop should be a problem. So the idea is to consider using this called this holonomy. So this holonomy is given by the solution of the following ODE. Formally, you can see the solution of this ODE when this H equals to 1 time S equals to 1. It just gives us this product of this exponential part. However, as this A is not a function but it's distribution, how to give a meaning to the solution to this ODE should be still a problem. One idea is, as I think, and how they used in their paper for the SPD is to using some idea from rough paths to give a meaning to to use the rough paths to understand this ODE as rough differential equations. Another idea is using by this driver's idea is to using this axial gauge. And I just explained for this FA component, it's just the white noise. So A is the integral of white noise. If we take this kind of integral, this part is just a martingale. So we can using this to understand this ODE and SDE, and use the SDE to give a meaning to this H. And in fact, the driver used this idea to find the joint law of this Wilson loop. So this is the definition for the 2D Mills model. And this is for the two-dimensional case. And now we want to go to this master loop equation. And we already find this loop is, we have different type of loop. If we fix the loop, if we fix this loop L, and this is our Wilson loop, and this Wilson loop will satisfy some recursive relations for different loops. So this means, for example, on the left we have the expectation of this Wilson loop, and on the right we have different operations for these loops. This is also called this Dyson-Springer equation, also called this Makeenko-Migdal equations. And here on the right, we give the different operations for this Wilson loop. Here we have 3 kinds of Wilson loop. This is only for this Lie group, is this U1. If we consider more generally groups like SU1 or SO1, we have other operations. And here we have this deformations part depending on this so-called negative deformation or positive deformation, and also splitting terms. And I will give the definition of these operations in next slide. And this kind of master loop equation, discrete, this master loop equation has been first proved by Chatterjee by using this Stein's method. So this is using this like the integration by parts formula to prove it. And later with Hausdorff, Scott, we're using this dynamics and Vital calculus to replace this Stein's method to give another proof of it. But in our both of this Chatterjee and our case, we consider some average type of this master loop equation. We need to take summations for all this bound E here. But later this result has been extended by Skychow and Park and Sheffield using this random surface representation. So in their case, this master loop equation, in fact, is more general. They can fix the bound, and this deformation they can just consider it for this fixed bound, and have this negative deformation or positive deformation as splitting part. And now I want to explain what is these operations. So this deformation is, for example, now we have this. This is our example of this loop, and E is our bound. And the deformation is just, in fact, is the interaction between this loop and the plicat. So if we start from the boundary of this loop, the positive deformation just go, for example, we start from here and go along this way. If we go here, then we will go along the boundary of this plicat first. And then we go along the original line of this loop. And then we go back. So this gives us this positive, so-called this positive deformation. And the negative deformation just also interaction of this loop with this plicat. But here we just need to change the orientation of this loop, the boundary of this plicat. So here, if we go along this way, we change the orientation, we go this way, and these two bonds they cancel with each other. So we get a new loop. So this is so-called this negative deformation part. And this is corresponding to our two part. And another example is called this splitting. The splitting part is for this interaction of this loop for more complicated loop. In fact, we have a loop written in the following way. We first go along this way. We go this E twice here. And splitting just means we split this complicated loops to two simple loops. This gives us a splitting part. And this is this splitting, and this master loop equation just gives us the expectation of general Wilson loop with given span on the right can be seen as a linear combination of this deformation part and splitting part. This is our discrete master loop equation. And we also have this continuum master loop equation. This is consider this L is a simple process. This is just our loop. For example, we write it in this, draw it in this way. But in fact, the loop can be more complicated. You can consider the loop. In fact, it can go to in a more very complicated way. But locally, the loop looks like if we start from this vertex V here, it go along this E1. Maybe it go other way, but then go back along this E4. And then go along this E2, and then we go in another way, and then go back, go along the inverse of E3 and go back to this V component. And here we have four faces, F1, F2, F3, and F4 here, four faces. And here this is our loops, and the important thing is this local properties of this loop. And the continuum master loop equation is written in the following way. So this means the expectation of this Wilson loop. On the left, we get the area derivatives of this expectation of this Wilson loop. This area derivatives is with respect to this Ti just equals to this area of each Fi here. And on the right, we also have this splitting part. So here we have the complicated loops. but we get two simple loops. One is 1, for example, starting from here, and then it go here. It gives a more simple loop, and another one, 2. So this master loop equation is very useful to calculate the expectation of this Wilson loop recursively. In fact, if we consider the larger limit, as I just mentioned, this Wilson loop will converge to some deterministic functions. So in this case, they have this factorization property for the larger limit. So we can split this expectation of this Wilson loop to 2 different expectations of simple loops. And we use these simple loops and these area derivatives, which can be used to calculate the expectation of this larger limit of this Wilson loop. And this kind of equations only depending on local behavior of these loops. If we consider if the loop becomes more complicated, it also satisfies the same master loop equation. And also first proposed by physicists, and they give some intuitive proof for it by this Makeenko and Migdal. And later, first rigorously proved by Terry Levy and Davis, and later by both Driver and Hall and Kemp and also Driver, they have using different approaches to give a proof for this master loop equation in a continuum case. And their techniques are also based on this Driver's formula and also integration by parts formula. So when we start to learn this master loop equation and prove this discrete master loop equation, one question to us is, what is the relation between this discrete one and the continuum one? This is our discrete one. Discrete one, this is our Wilson loop. We have the expectation of the Wilson loop. And on the right, we have this deformation part. But here, this is positive deformation minus some negative deformation. We have a splitting part. This is our discrete one. And for the continuous one, we also, in fact, have this splitting part. So in fact, when we start to consider it, we will think this kind of splitting part should converge to this continuum splitting part. The rest part should go to this area derivatives. So formally, it looks like this deformations, as I just mentioned. Looks like this deformation part. Looks like it adds some area or lose some area for these loops. So it should go to the derivatives of these loops. So our main result is also this type. We just prove that our main result is if we consider a loop with just a simple crossing. This is a local starting from this V here and go along this E1 as I just mentioned, and go back along this E4 and go to E2 and go back along the inverse of E3. And we can have the lattice approximation to this kind of loop written in the following way. You can find it. And for this kind of continuum one, we have unified this master loop equation. But for the lattice case, in fact, for different bound, we have different master loop equations. For example, if we choose a bound is this E epsilon, this E epsilon can be viewed as lattice approximation to this vertex V here. And we will go it twice here. So in this case, if we consider this master loop equation with respect to this bound, now we have this deformation part, and we also have this splitting part. But if we consider this bound like this E1, we only go it once, then we only have the deformation part without this splitting part. So if we want to prove this kind of discrete model, this discrete master loop equation convergence to the continuous one. So our main result is if we consider the general lattice approximation to this to this loop with a simple crossing, and then we have a general rule to select the bounds in this lattice approximation.
such that some suitable linear combinations of these discrete master loop equations will converge to this continuum one. So this is our main results for this master loop equations. And now I want to give some ideas of how we prove this kind of result. And in fact, to prove this result, and I just compare with the discrete one, the continuum one, we find here in both cases we have the splitting part. So we need first to prove this discrete, this splitting part will converge to this continuum splitting part. This in fact is very easy by using this driver's formula. So as I just mentioned, recall using this driver's formula at this actual gauge, driver has derived the expectation of this Wilson loop can be represented by the product of this, in fact, of this heat kernel. So here, if we consider this is the Wilson loop, and here this is like the trace of this QL, and we have an extra density part here. This density depending on the heat kernel of this Laplace operator. And here this F just means if we consider a loop is like a graph, and this face F is just the face formed by the in this graph, and take the product for all this face. And here we consider this heat kernel. That we use this area of this face to change to replace this time for this heat kernel. And here the value of this heat kernel is this the boundary along this face, the holonomy along this boundary of the face, just this H component. And this is the continuous version of this driver's formula. So in the discrete one, we also have the discrete version of this driver's formula. So in this case, we just can replace this heat kernel by this convolution of these Wilson actions. So in this case, this S epsilon, we can see it's just this this action functions. But in this case, we can just view it as a transition probability from this identity to Q for the random walk. So this S epsilon K just this K-fold convolutions of this S epsilon. So in this case, we can see this kind of random walk should go to this Brown motion part. So this gives us the convolution of this S epsilon should converge to this heat kernel. So this means this discrete, this Wilson loop will converge to this continuous one. So this implies easily we can say the product of this Wilson loop will converge to the discrete one will converge to the continuous one. So this gives us a corresponding splitting part will converge to each other. So this gives us the convergence of the splitting part. If we use the equation directly, we can see this gives us the other part, the deformation part, should converge to some area derivatives. But here we want to give a more direct proof of it to see the continuum limit of each deformations. So here is our deformation. If we consider this is our lattice approximation for the loop, and now we consider an example of our deformation. Here this is our negative deformations. Here maybe we start from here. And the negative deformation just means if we go along this way, we will not repeat the original line of this E epsilon, but we will go along this red line and then go along to this E1 E2. So in this case, we have a low loop, this negative deformation. And we also have another so-called this positive deformation. So for the positive deformation, if we go along this way, as I just mentioned, we will go along this edge and repeat this red line, go the inverse direction of this red line. And then we go along this E component and then go along E1, E4. This gives us another new loop. So this is like so-called this positive deformation. And for each kind of phase of F1, F2, F3, and F4, we have different, we have all these positive deformation and negative deformations. And we can prove
this kind of discrete, this deformation part will in fact converges to the gradient, the inner product of the gradient of this trace and the gradient of this P for this of this kit kernel on this T4 corresponding to the area of this F4 here. And based on this and the local behavior of this vertex V here, this also gives us the formula for this, like this I4, and using the integration by parts formula, this gradient will give us a Laplacian operator. And this Laplacian, by using this kit kernel, will give us this area derivatives, and also gives us some counter terms. And in fact, we need to use these linear combinations, choose linear combinations suitably to cancel all these counter terms. And finally, this will give us the correct this master loop equations written in to written this way here. This is our so the basic idea for our proof is to identify this the limit of this deformation part, and we need to use this deformation to have this area derivatives to finally get our continuum master loop equation. And to prove this kind of result, we also use this driver's formula. In fact, we use this driver's formula to write it in the following way. We also use this discrete, this SE epsilon, and also this convolution of this Wilson actions. And we can write this this negative deformation and positive deformation in terms of the following integrals. And when that epsilon goes to 0, we can prove this kind of integral will converge to this kind of derivatives of this, the first component of this trace, and also the derivatives of this kit kernel. And now if we take the integrals of this will give us the gradient of this trace component and also this kit kernel part. So this is a very important result to help to us to identify the limit of this deformation part. And to prove this, we're using this Kita-Weil spectral theorem to decompose this convolution of this this transition probability in terms of some irreducible characters. So in this case, for this Lie group, if we consider this irreducible characters, this plays the same role as this eigenfunctions of these Laplacian operators. So it's like using spectral decomposition for these terms. We can replace this part by some irreducible characters. And to prove this kind of convergence, we're using the following Gaussian approximation lemma for the functions on this Lie group. In fact, if we consider this Wilson actions as S epsilon, we will say this S epsilon will make this Q closely identical with large probability. So if we calculate this kind of integral, we can decompose this S epsilon to small scales and large scales. For small scale part, SQ we can use because it's close to identity. We can view this S epsilon Q as some Lie algebra value Gaussian integral. And for this, and then we're using some Taylor expansion for this FQ component. And for the large scales part, in fact, it's just the error part. And for the small scale part, we're using this Gaussian integral and also the Taylor expansion for this F component. We can prove that kind of result. And based on it, we can calculate to prove this kind of lemma. And this helps us to identify the limit of this deformation part and to prove this result. And this is all I want to say here. Okay, thank you.